Alright everybody, this is the first video for Tuesday, April 28th. I am recording this before the survey results are all in, so just stay tuned for a Canvas announcement tomorrow. Well, I guess Friday, I should say, regarding what time we'll be meeting for class on Tuesday. Couple of little funnies for you guys. I kind of want this t-shirt now. We'll talk about this at the very end, van der Waals equations for non-ideal gases. And then we don't get to talk about it as much as they do in physics, but the buoyancy of various gases is dependent on comparing their densities. So literally balloons with helium in them rise, which, every child knows, just for birthdays being so important and such. But any gas that's less dense than air will rise. Alright, so kind of a preview of where we're going. We have a few topics from 9.3 to pick up, but then we're mostly going to be in 9.4 through 9.6, effusion, diffusion, kinetic molecular theory, which is one of my favorite concepts probably, and then non-ideal gas behavior. So the equation that was on that t-shirt. So the last couple of things from 9.3 we need to talk about are partial pressure, collecting gases over water, and the mole fraction. Partial pressure is this idea that the total pressure in a mixture is the sum of pressures from each of the constituent parts. It doesn't seem that groundbreaking, but it does assume that the mixture is the sum of its parts, rather than, oh, you mix helium with oxygen and they interact and the pressure is somehow lower. Gases are unique in this way because actually when we dissolve a solid in a liquid, we don't get something that's the volume of the two things together, right? The solid actually kind of filters in amongst the water molecules in different orientations and takes up less space. Same thing when we make metal alloys. We don't just have a volume plus a volume or something like that. Steel is actually made because carbon atoms can fit between the atoms of iron and copper and whatever else is in your mixture. Mostly iron, but gases, because in the ideal world where we live most of the time, they don't interact with each other, we add them up, we could visualize it as if only the blue particles were in there, the same volume at the same temperature and pressure, or the same volume at the same temperature, they would exert this amount of pressure, 300 kilopascals. If it was just the purple in there, 600. If it was just the yellow in there, 450. And so we can kind of think about them as separating out, and it'll be the sum of the pressures. So an example kind of practice problem of what we might see happen. In scuba tanks, helium is mixed with oxygen to help prevent the bends. So by mixing it with a less dense gas, helium is less dense than oxygen. It helps out with that. We're not interested in the physiology at this point. We just want to know about this idea of partial pressure. So for a particular dive, we started with 46 liters of helium at 25 degrees Celsius and 1 atmosphere. and 12 liters of oxygen at 25 degrees Celsius in 1 atmosphere. And we pump them and compress them into the scuba tank. So we're going to calculate the partial pressure of each gas in that scuba tank. So we're starting off with kind of a semi-complicated problem, but I think you guys will be able to follow it. Okay, so let's get my pen out. We'll just circle some of the things. For helium, we've got volume, temperature, pressure. These are the initial conditions. And for oxygen, we have a volume, a temperature, and a pressure. And then as far as the total gas canister that has helium and oxygen in it, it'll be 5 liters. Calling that V total. And it's also at 25 degrees Celsius. So we're going to actually use the temperature being consistent to help us in solving this equation, or this problem I should say. Here's Dalton's law. The partial pressure of helium plus the partial pressure of oxygen is equal to the total pressure in the tank at the end of the day. What we're given in the problem are not the partial pressures. We're given the pressures and the volumes in the amounts that are then compressed to go into the tank. So I'm just going to write out some of the info from the problem that's in the slide. Pink is going to be helium and green is going to be oxygen. So all these values are before we put the helium in the tank. So originally we've got 46 liters of helium, but we're going to squeeze that in to 5 liters in our final compression tank. Similarly, we have oxygen with these initial conditions. And whenever I'm talking about initial and final conditions, that's a clue that we need to use the combined gas law to solve our problem. The question's asking what's the pressure total. Here we have the before conditions. There's a kind of a long way we could solve this. We could solve for moles of each gas, go back around after adding the moles to each other, and calculate the total pressure. But since we have this idea of partial pressures, we can actually take a slight shortcut and solve for the pressure the helium would be in the total gas canister. So what that means is that we're compressing helium into the 5 liter space. So if I solve for pressure final of helium, that's the partial pressure of helium completely independent of what the oxygen is doing. And same thing for the oxygen. It's originally in 12 liters of space, and I'm compressing it down to 5 liters of space. And so then at the end of the day, I can just add the partial pressures and get the total pressure. So do helium first. Here's the combined gas law. I guess it's the same amount of work. You could solve for moles on both, add them, and then solve for pressure, but this helps us kind of get the idea of partial pressure across. For helium, the moles and the temperature are both the same. Initial pressure is 1 atmosphere, initial volume is 46 liters. I'm compressing it to a final partial pressure in 5 liters of space. So when we solve for P final, which is the same as the partial pressure of helium, we get 9.2 atmospheres. So now if we solve for the partial pressure of oxygen, moles and temperature are the same. So I'm just going to do PV equals PV. Final volume, 5 liters is the canister. This final pressure is the partial pressure of oxygen. So if you're visualizing it, just think about taking oxygen and compressing it, taking helium and compressing it, and then we smush those two things into the same 5-liter canister. So now I'm going to solve for P total, which is the pressure in the scuba tank. And we're just going to add those pressures. And we get 11.6 atmospheres. It is 3 sig figs because the partial pressures have 2 sig figs, and then when we add we keep to the 10th place, so 11.6 atmospheres. So partial pressures also leads us to this idea of thinking about the relative amounts of the components of the mixtures. So if you look, just compare the blue to the yellow canisters in here. Gas B, whatever it is, there's much fewer particles in there. You can kind of just visually see there's more yellow particles in the tank. It's harder to see it here, but it's true here too. And the partial pressure from yellow is higher than the partial pressure from blue. And that's because there's more yellow in there. So partial pressure is actually proportional to the number of moles of gas in the mixture. And what that leads us to is this idea of the mole fraction, which is actually described here, but I'll go into it in more detail in the next slide. Moles of the gas of interest over the total number of moles of gas in the particle, in the sample. And partial pressure of each gas is actually related to the total pressure by their mole fractions. So if we look at all of the mole fractions in a sample, it'll correlate to how much pressure is due from each gas. So each gas contributes a weighted amount of pressure based on how much of the mixture is them. Alright, so mole fractions and mole percents. So mole fractions are represented by the Greek letter chi. It's a fancy sort of scripty S, X. I think we use the uppercase chi technically, but that's not super important. So gas A, or chi sub A, is equal to the number of moles of A over the total moles that's in the gaseous mixture. Another way of writing that is by saying, oh, it's moles of A plus moles of B plus moles of C, however many species there are in our gaseous mixture. All of the mole fractions in a sample will add up to 1. It's kind of like percents that add up to 100. And actually, to find the mole percent, you just take the mole fraction and times it by 100. But it's the same concept where we take the part over the whole. And then if you want the percent, you multiply by 100. But most of the time, we'll stick with the fractions. So going back to the mole fraction being the part over the whole, we've got chi sub A is equal to